Gödel's completeness theorem is a fundamental result in mathematical logic, specifically in the realm of first-order logic. It was first proven by Kurt Gödel in 1929. This theorem establishes a crucial link between semantic truth and syntactic provability. Let's break down the theorem and its implications in detail. 1. First-order logic. First-order logic, FOL, is a formal system used in mathematics, philosophy, linguistics, and computer science. It includes variables, represent objects in a domain, quantifiers, for all, turned A, and there exists, predicates, functions that return true or false, logical connectives, and, or, not, implies. 2. Semantic truth versus syntactic provability. Semantic truth, a statement is semantically true if it holds in every model of the theory. A model is an interpretation of the theory where the axioms and theorems are true. Syntactic provability, a statement is syntactically provable if there is a formal proof of the statement using the axioms and inference rules of the theory. 3. Statement of the theorem. Gödel's completeness theorem states that for any first-order theory T, and any statement \phi if \phi is true in every model of T, i.e. \phi is semantically true, then \phi is provable from T, i.e. \phi is syntactically provable. In simpler terms, if a statement is true in all possible interpretations, models, of a theory, then there is a formal proof of that statement using the axioms of the theory. 4. Implications of the theorem. Completeness. The theorem shows that first-order logic is complete, meaning that all semantically true statements are also syntactically provable. Soundness. The converse is also true and is known as the soundness theorem. If a statement is syntactically provable, then it is semantically true. Model theory and proof theory. The theorem bridges the gap between model theory, study of models, and proof theory, study of formal proofs. 5. Proof outline. Gödel's original proof involved several key steps: Henkin's construction, introduce Henkin constants to ensure that every existential statement has a witness. Maximal consistent set, extend the set of axioms to a maximal consistent set, where every statement or its negation is included. Constructing a model, use the maximal consistent set to construct a model where all axioms and theorems hold. 6. Historical context and developments. Gödel's incompleteness theorems. While the completeness theorem deals with first-order logic, Gödel's incompleteness theorems, proven later, show limitations in higher-order logics and arithmetic. Henkin's simplification. Leon Henkin simplified Gödel's proof in his PhD thesis, making it more accessible and widely understood. 1. 7. Applications and extensions. Automated theorem proving. The theorem underpins many automated theorem proving systems, which rely on the completeness of first-order logic. Model theory. It has profound implications in model theory, influencing the development of various logical frameworks and systems. Philosophical implications. The theorem has philosophical implications regarding the nature of mathematical truth and provability. Conclusion. Gödel's completeness theorem is a cornerstone of mathematical logic, demonstrating that first-order logic is both sound and complete. It ensures that all semantically true statements can be formally proven, providing a robust foundation for logical reasoning and formal systems. Henkin constants. Henkin introduced new constants, called Henkin constants, to the language of the theory. These constants serve as witnesses for existential statements. For every existential formula \exists x, \phi x, a new constant c_\phi is introduced, and the formula \phi c_\phi is added to the theory. 2. Maximal consistent set. The next step is to extend the theory to a maximal consistent set. A set of formulas is consistent if no contradiction can be derived from it. A set is maximal consistent if it is consistent, and adding any new formula would make it inconsistent. This is achieved through the following steps: enumerate all formulas, list all formulas in the language. Extend the theory for each formula \phi. If adding \phi to the theory keeps it consistent, add \phi. If not, add \neg\phi. 3. Constructing the model. Using the maximal consistent set, a model is constructed where domain, the domain of the model consists of the Henkin constants. Interpretation of constants. Each constant is interpreted as itself. Interpretation of functions and predicates, defined in such a way that all axioms and theorems of the theory hold true in this model. 4. Ensuring satisfaction of formulas. The construction ensures that every formula in the maximal consistent set is satisfied in the model. This involves atomic formulas directly satisfied by the interpretation. Complex formulas. Satisfaction is ensured by the consistency and maximality of the set. 5. A completeness proof. The completeness proof shows that if a formula is true in every model of the theory, semantically true, then it is provable from the theory, syntactically provable. Henkin's construction provides a method to build a model where the theory holds, thereby demonstrating that any semantically true formula can be proven within the theory. Example: consider a simple theory with the following axioms: \forall x, p, x, \right arrow q, x, \exists x, p, x. Using Henkin's construction, introduce a Henkin constant, c, for the existential statement, \exists x, p, x, and add p copyright symbol to the theory. Extend the theory to a maximal consistent set, ensuring that for every formula, \phi, either \phi or \neg\phi is included. Construct a model where the domain consists of the constant, c, and interpret p and q such that the axioms hold. This process ensures that the theory is complete, meaning any semantically true statement can be proven within the theory. Henkin's construction is a powerful tool in logic, providing a concrete method to demonstrate the completeness of first-order logic. Gödel's incompleteness theorems are two of the most profound results in mathematical logic, proven by Kurt Gödel in 1931. These theorems reveal fundamental limitations in formal systems that are capable of expressing basic arithmetic. 1. First incompleteness theorem. Statement: the first incompleteness theorem states, no consistent formal system that is capable of expressing elementary arithmetic can be both complete and consistent. Specifically, in any such system, there are true statements about natural numbers that cannot be proven within the system. Key concepts: formal system, a set of axioms and rules of inference used to derive theorems. Consistency, a system is consistent if it does not derive any contradictions. Completeness, a system is complete if every true statement can be derived within the system. Proof outline. Gödel's proof involves several ingenious steps: arithmetization of syntax, Gödel encoded statements, proofs, and the process of proving within arithmetic itself. This is known as Gödel numbering. Self-referential statements. Gödel constructed a statement, G, that essentially says, this statement is not provable within this system. This is a self-referential statement. Diagonalization. Using a technique similar to Cantor's diagonal argument, Gödel showed that if G were provable, it would lead to a contradiction. Therefore, G is true but not provable within the system. Implications. Limitations of formal systems. There are always true statements that lie beyond the reach of formal proof in any sufficiently powerful system. Impact on Hilbert's program. This theorem showed that David Hilbert's goal of finding a complete and consistent set of axioms for all of mathematics is unattainable. 2. Second incompleteness theorem. Statement: the second incompleteness theorem states, no consistent formal system that is capable of expressing elementary arithmetic can prove its own consistency. Key concepts. Self-referential consistency statement. The theorem constructs a statement within the system that asserts the system's own consistency. Extension of the first theorem. This theorem builds on the first by showing that the system cannot internally verify its own consistency without leading to a contradiction. Proof outline. Formalizing consistency. Gödel formalized the notion of consistency within the system. Self-reference. He constructed a statement that asserts the system's consistency. Incompleteness. Using the first incompleteness theorem, Gödel showed that if the system could prove its own consistency, it would be inconsistent. Implications. Foundational impact. This theorem has profound implications for the foundations of mathematics, showing that any system complex enough to include arithmetic cannot demonstrate its own consistency. Philosophical consequences. It raises questions about the nature of mathematical truth and the limits of formal reasoning. 3. Historical context and developments. Hilbert's program. Gödel's theorems were a response to Hilbert's program, which aimed to formalize all of mathematics in a complete and consistent set of axioms. Subsequent work. Gödel's work influenced many areas of logic and mathematics, including Tarski's undefinability theorem, Church's proof of the unsolvability of the Intschiedungs problem, and Turing's halting problem 12. 4. Applications and extensions. Mathematical logic. Gödel's theorems are foundational in the study of mathematical logic and the philosophy of mathematics. Computer science. They have implications for the limits of computation and formal systems in computer science. Philosophy. The theorems have been discussed extensively in the context of the philosophy of mind and artificial intelligence. Conclusion. Gödel's incompleteness theorems demonstrate the inherent limitations of formal systems in mathematics. They show that no system capable of expressing basic arithmetic can be both complete and consistent, and that such a system cannot prove its own consistency. These results have had a profound impact on mathematics, logic, and philosophy, highlighting the limits of formal reasoning and the complexity of mathematical truth. Relationship between the theorems. Scope and domain. Completeness theorem applies to first-order logic, which deals with the relationship between semantic truth and syntactic provability in first-order theories. Incompleteness theorems apply to formal systems that include arithmetic, showing limitations in what can be proven within such systems. Complementary nature. Completeness theorem ensures that first-order logic is robust in that all semantically true statements can be proven. Incompleteness theorems highlight the limitations of formal systems, showing that no system capable of arithmetic can be both complete and consistent. Different levels of logic. First-order logic. The completeness theorem applies to first-order logic, which is less expressive than higher-order logics. Arithmetic and beyond. The incompleteness theorems apply to systems that can express arithmetic, which are more expressive and thus subject to greater limitations. 4. Implications for formal systems. First-order logic. Gödel's completeness theorem provides a solid foundation for first-order logic, ensuring that it is both sound and complete. Arithmetic and higher-order systems. Gödel's incompleteness theorem show that more expressive systems, such as those capable of arithmetic, cannot achieve the same level of completeness and consistency. Conclusion. Gödel's completeness theorem and incompleteness theorems address different aspects of formal systems. The completeness theorem assures us that first-order logic is complete and sound, while the incompleteness theorems reveal the inherent limitations of more expressive systems, such as those capable of arithmetic. Together, these theorems provide a comprehensive understanding of the capabilities and limitations of formal logical systems. Automated theorem proving. Automated theorem provers. The completeness theorem underpins the development of automated theorem proving systems. These systems use algorithms to prove or disprove statements within a formal system. Since first-order logic is complete, these systems can, in principle, find proofs for all semantically true statements. Applications. Automated theorem provers are used in software verification, hardware design, and artificial intelligence to ensure the correctness of systems and algorithms. 2. Model theory. Model construction. The theorem provides a method for constructing models of first-order theories. This is crucial in model theory, a branch of mathematical logic that studies the relationships between formal languages and their interpretations or models. Applications in mathematics. Model theory is used in various areas of mathematics, including algebra, geometry, and number theory, to understand the properties of mathematical structures. 3. Formal verification. Software and hardware verification. Formal verification involves proving the correctness of algorithms and systems with respect to a formal specification. The completeness theorem ensures that if a specification is consistent, all true properties can be formally verified. Safety-critical systems. This is particularly important in safety-critical systems, such as aerospace, automotive, and medical devices, where ensuring correctness is vital. 4. Philosophical implications. Nature of mathematical truth. The theorem has philosophical implications regarding the nature of mathematical truth and provability. It shows that for first-order logic, truth and provability are equivalent, which has been a topic of discussion in the philosophy of mathematics. Foundations of mathematics. It contributes to our understanding of the foundations of mathematics, particularly in the context of formal systems and their limitations. 5. Education and pedagogy. Teaching logic. The completeness theorem is a fundamental result taught in courses on mathematical logic and theoretical computer science. It helps students understand the relationship between syntax, formal proofs, and semantics, truth in models. Critical thinking. Understanding the theorem and its proof enhances critical thinking and problem-solving skills, as it involves deep logical reasoning and the construction of formal arguments. 6. Artificial intelligence. Knowledge representation. In AI, the theorem supports the development of knowledge representation systems that use first-order logic to encode information. These systems can reason about the information and derive new knowledge. Expert systems. Theorem provers based on first-order logic are used in expert systems to make logical inferences and provide decision support in various domains, such as medicine, finance, and law. Conclusion. Gödel's completeness theorem has far-reaching implications in both theoretical and practical domains. It provides a solid foundation for automated reasoning, model theory, formal verification, and more. Understanding this theorem helps in appreciating the power and limitations of formal systems and their applications in various fields. Limitations of formal systems. First, incompleteness theorem. Statement: in any consistent formal system that is capable of expressing elementary arithmetic, there are true statements about natural numbers that cannot be proven within the system. Implication: this theorem shows that no matter how comprehensive a formal system is, there will always be true statements that lie beyond its reach. This challenges the notion that mathematics can be fully captured by a single, complete set of axioms. Second incompleteness theorem. Statement: no consistent formal system that is capable of expressing elementary arithmetic can prove its own consistency. Implication: this means that a system cannot use its own axioms and rules to demonstrate its consistency. This has significant implications for the foundations of mathematics, as it shows that the assurance of consistency must come from outside the system. 2. Impact on Hilbert's program. Hilbert's program. David Hilbert aimed to formalize all of mathematics in a complete and consistent set of axioms and to prove the consistency of these axioms using finitary methods. Implication: Gödel's incompleteness theorem showed that Hilbert's program is unattainable. No formal system that includes arithmetic can be both complete and consistent, and such a system cannot prove its own consistency. This was a major setback for the foundational goals of mathematics in the early 20th century. 3. Philosophical implications. Nature of mathematical truth. The theorems suggest that mathematical truth is not solely a matter of formal derivation from axioms. There are true mathematical statements that cannot be proven within any given formal system, indicating that mathematical truth transcends formal proof. Platonism versus formalism. The theorems have fueled debates between different philosophical views of mathematics. Platonists, who believe in an objective mathematical reality, see the theorems as evidence that mathematical truths exist independently of formal systems. Formalists, who view mathematics as a creation of formal systems, must grapple with the limitations imposed by the theorems. 4. Implications for computer science. Limits of computation. The theorems imply that there are inherent limits to what can be computed or decided by algorithms. This is closely related to the concept of undecidability in computer science, where certain problems cannot be solved by any algorithm. Artificial intelligence. The theorems suggest that there are limits to what can be achieved by artificial intelligence, particularly in terms of reasoning and proving mathematical truths. This has implications for the development of AI systems that aim to replicate human reasoning. 5. Impact on logic and proof theory. Proof theory. Gödel's theorems have led to the development of proof theory, which studies the nature and structure of mathematical proofs. The theorems highlight the need for alternative approaches to understanding and formalizing proofs. Model theory. The theorems have influenced model theory, which studies the relationships between formal languages and their interpretations. Model theory explores the limitations and capabilities of different formal systems in capturing mathematical truths. 6. Extensions and related results. Tarski's undefinability theorem. Alfred Tarski's theorem states that the truth of arithmetic statements cannot be defined within arithmetic itself. This result is closely related to Gödel's theorems and further underscores the limitations of formal systems. Church-Turing thesis. The theorems are related to the Church-Turing thesis, which posits that any effectively calculable function can be computed by a Turing machine. Gödel's theorems imply that there are limits to what can be computed, reinforcing the thesis. Conclusion. Gödel's incompleteness theorems have far-reaching implications for mathematics, logic, computer science, and philosophy. They reveal the inherent limitations of formal systems, challenge foundational programs, and influence our understanding of mathematical truth and computation. These theorems continue to shape research and thought in various fields, highlighting the complexity and depth of formal reasoning. Gödel numbering. Definition. Gödel numbering is a method of encoding mathematical and logical statements, proofs, and symbols as unique natural numbers. This encoding allows statements about mathematics to be transformed into statements about numbers. Process. Assigning numbers, each symbol in the formal language, variables, constants, logical connectives, etc., is assigned a unique natural number. Encoding formulas. Complex formulas and sequences of symbols are encoded as unique numbers by combining the numbers assigned to their constituent symbols in a specific way. Example. Suppose we have a simple formal language with symbols \forall, \exists, \wedge, \v, \neg, equals 0, 1, 2, \lets. Each symbol is assigned a unique number. \forall might be assigned the number 1. \exists /might be assigned the number 2, \wedge might be assigned the number 3, and so on. A formula like \forall x, p, x, \right arrow q, x would be encoded as a unique number based on the numbers assigned to each symbol. 2. Self-reference. Concept. Self-reference occurs when a statement refers to itself. In the context of Gödel's theorems, self-referential statements are those that make assertions about their own provability or unprovability. Construction. Gödel ingeniously constructed a self-referential statement using Gödel numbering. He created a formula, G, that essentially says, this statement is not provable within this system. This is achieved through a process called diagonalization. Diagonalization is a technique used to construct self-referential statements. Gödel used it to create a statement that refers to its own Gödel number. The statement G is constructed such that it asserts its own unprovability. Let \phi x be a formula that expresses x is the Gödel number of a formula that is not provable. Gödel constructed a specific number G such that \phi G is the statement the formula with Gödel number G is not provable. 3. Relation to the incompleteness theorems. First incompleteness theorem. Self-referential statement. Gödel's first incompleteness theorem relies on the construction of a self-referential statement, G, that asserts its own unprovability. Gödel numbering. By encoding the syntax of the formal system into numbers, Gödel was able to create a statement that refers to its own Gödel number and thus to itself. Proof. Gödel showed that if G were provable, it would lead to a contradiction, since G asserts its own unprovability. Therefore, G is true but not provable within the system. Second incompleteness theorem. Consistency statement. The second incompleteness theorem involves constructing a statement that asserts the consistency of the formal system. Self-reference. This statement is also self-referential, as it makes an assertion about the system's ability to prove its own consistency. Gödel numbering. The encoding of the consistency statement and the formal system's axioms into numbers is crucial for constructing this self-referential statement. Conclusion. Gödel numbering and self-reference are fundamental to the proofs of Gödel's incompleteness theorems. Gödel numbering allows the encoding of syntactic elements into numbers, enabling the construction of self-referential statements. These self-referential statements are at the heart of the incompleteness theorems, demonstrating the limitations of formal systems in proving all true statements and their own consistency. Constructing the self-referential statement. Step-by-step process. Encoding syntax. Assign unique numbers to each symbol in the formal language, for example, variables, logical connectives, quantifiers. Encoding formulas. Combine these numbers to encode entire formulas and sequences of formulas. Provability predicate. Define a formula, \text prof x, that expresses x is the Gödel number of a provable formula. This formula itself is encoded as a number. Diagonalization. Gödel used a technique called diagonalization to construct a self-referential statement. Here's a simplified outline. Define a formula, \phi x, let \phi x be a formula that expresses x is not the Gödel number of a provable formula. Diagonalization. Construct a specific number, G, such that \phi G is the statement the formula with Gödel number G is not provable. 3. The self-referential statement. The statement G constructed by Gödel is G \equiv \neg \text prof \ulcorner G \urcorner. Here, \ulcorner G \urcorner denotes the Gödel number of the statement G. Thus, G asserts its own unprovability. 4. Implications. If G is provable, if G were provable, then \text prof \ulcorner G \urcorner would be true, which contradicts G's assertion that it is not provable. If G is not provable, then \neg \text prof \ulcorner G \urcorner is true, meaning G is true but not provable. Example in simple terms. To illustrate with a simpler analogy, consider the statement, this statement is false. If the statement is true, then it must be false, which is a contradiction. If it is false, then it is true, which is also a contradiction. This self-referential paradox highlights the complexity and limitations of formal systems. Conclusion. Gödel's construction of a self-referential statement is a brilliant example of how self-reference can be used to demonstrate the limitations of formal systems. By encoding statements and their provability within the system, Gödel showed that there are true statements that cannot be proven within the system, leading to his incompleteness theorems. Early 20th century mathematics. Hilbert's program. In the early 20th century, David Hilbert proposed a program to formalize all of mathematics. His goal was to find a complete and consistent set of axioms for all mathematical truths and to prove the consistency of these axioms using finitary methods. Formal systems. Mathematicians were working on formalizing various branches of mathematics using axiomatic systems. The aim was to ensure that all mathematical truths could be derived from a well-defined set of axioms. Gödel's background. Education and influences. Kurt Gödel studied at the University of Vienna, where he was influenced by the Vienna Circle, a group of philosophers and scientists focused on logical positivism and the foundations of mathematics. Doctoral thesis. Gödel's doctoral thesis, completed in 1929, was on the completeness of first-order logic, which later became known as Gödel's Completeness Theorem. 2. Development of the Incompleteness Theorems. Gödel's insight. Arithmetization of syntax. Gödel realized that statements about mathematical objects could be encoded as statements about numbers. This process, known as arithmetization, allowed him to translate metamathematical statements into arithmetic. Self-reference. Gödel used a technique called diagonalization to construct self-referential statements. This was inspired by Cantor's diagonal argument and Richard's paradox. The proofs. First Incompleteness Theorem. Gödel constructed a statement, G, within a formal system that essentially says, this statement is not provable within this system. He showed that if G were provable, it would lead to a contradiction, thus G is true but not provable within the system. Second Incompleteness Theorem. Building on the first theorem, Gödel showed that a formal system capable of expressing elementary arithmetic cannot prove its own consistency. This was achieved by constructing a statement that asserts the system's consistency and demonstrating that if the system could prove this statement, it would be inconsistent. 3. Publication and reception. Publication. Original paper. Gödel's results were published in 1931 in a paper titled Über formal unentschiedbare Sätze der Principia Mathematica und Verwandte System I, on formally undecidable propositions of Principia Mathematica and related systems I. Impact. The publication of Gödel's paper had an immediate and profound impact on the field of mathematical logic and the philosophy of mathematics. Reception. Mathematical community. Gödel's theorems were initially met with astonishment and skepticism. However, as the proofs were scrutinized and verified, the significance of his results became widely recognized. Philosophical implications. The theorems had far-reaching implications for the philosophy of mathematics, challenging the foundational goals of Hilbert's program and influencing subsequent philosophical debates about the nature of mathematical truth and provability. 4. Impact and legacy. Foundations of mathematics. Hilbert's program. Gödel's theorems demonstrated that Hilbert's goal of a complete and consistent formalization of all mathematics was unattainable. This led to a revaluation of the goals and methods of foundational research in mathematics. Formal systems. The theorems highlighted the inherent limitations of formal systems, showing that no system capable of expressing arithmetic can be both complete and consistent. Subsequent developments. Proof theory and model theory. Gödel's work influenced the development of proof theory and model theory, two branches of mathematical logic that study the nature of mathematical proofs and the relationships between formal languages and their interpretations. Computer science. The theorems have implications for computer science, particularly in the areas of computability and complexity theory. They underscore the limits of what can be computed or decided by algorithms. Conclusion. Gödel's Incompleteness Theorems, created in 1931, revolutionized our understanding of formal systems and the foundations of mathematics. By demonstrating the inherent limitations of formal systems capable of expressing arithmetic, Gödel's work had a profound impact on mathematics, logic, computer science, and philosophy. His theorems continue to influence research and thought in these fields, highlighting the complexity and depth of formal reasoning. That was all. Goodbye.